Thank you very much. Yes, this you would see from the title already that this is a little broader than quantum gravity. So it is a series. I will have a series of talks about the general status of fundamental physics today. And of course, quantum gravity and the epistemic status of quantum gravity is at the very center of this. So it is the crucial part of this. But I think it is important to think about the overall situation physicists find themselves in broader terms. So what I want to do is, today, I want to present a kind of a cartography of fundamental physics today. So this will be highly rushed, let's say, lots of different theories pointed at and none of them actually explained. But it is important to have this, I think, in order to see the overall scope of what's going on. Tomorrow then, I will talk in the first lecture about this feeling of uncertainty and kind of maybe crisis in the field that is palpable right now. So there is this feeling, no doubt. Different physicists, different observers have very different reading of that and very different understanding of the intensity of the problem. But it's clear that there is something that is disconcerting about the current situation. In the third lecture, then, I will discuss a perspective on this that, on my understanding, is helpful for having a better understanding of all this, a more adequate perspective on this, and this will have to do with meta-empirical theory assessment. In the fourth lecture, then, provided that there is enough time, because we may run into the fourth lecture already with the previous program, I will point at two other aspects of the issues of quantum gravity that are, I think, quite interested and are quite closely and intricately related to these epistemic issues. So that's roughly the program. What I want to do, however, before I delve into this program, is I want to give an improvised response to a question that Karen raised in her in her lectures. She raised the question: why actually is the idea of unification so powerful in physics? Is it such a strong driving force, in particular in quantum gravity? And of course, in quantum gravity, behind quantum gravity, there is this idea that one should find a unified description of gravity and the interactions that are relevant at microphysical scales when we test them. So unification is a strong driving force here. And it is a very good and very important question. Why is this so important? Why is this so crucial in the process of physics? And my view on this is that, first, it is so prominent because it works so well. And second, it is a hugely remarkable observation about our world that it works so well. And in order to understand this, we should think for a moment about the conventional understanding or approach towards unification or generalization or this category of approaches in our everyday world. And in our everyday world, the situation is of a kind that if we are more general about characterizing something, we are less specific, we are less precise. So if we decide to have a general statement about something, we are in a kind of zero-sum game, right? So we decide that we want to be more general even though we are less precise because for various reasons. It may be quite instructive to have general statements about a situation. Or I decide being less general because I want to be more precise. And the crucial point about physics that has been established time and again since Newton, actually, is that in physics, in fundamental physics at any rate, and in many contexts of formal science, other contexts of formal sciences as well, the more general, more unified theory at the same time is the more precise one. So what works in physics so often is that if we have different domains that are characterized by different theories, these domains are kind of influenced by the physics that is actually based in the other domain. And so there are some perturbations, some imprecisions in the characterization of the first domain by the first theory that are due to the other domain. And therefore, if that's the constellation, and if there is a coherent theory that covers both domains, the coherent theory of both domains unifies, and in unifying actually reduces these imprecisions. And this is something that doesn't have to be the case at all, right? It is not something that is trivial. In our everyday world, it doesn't happen most of the time. It may also be the case that there are theories that live next to each other, besides each other. They don't disturb each other, but they don't help each other either. If you think about Newtonian physics, for example, Newtonian mechanics, and classical electrodynamics, they live next to each other, right? So it's fine to describe the world in the 19th century, late 19th century, let's say, by using both theories and say, okay, that's the full story. And there is no full unification needed to do that. However, that's a kind of an unusual situation. It is more often than not, there are those interactions, interrelations between different domains. And the history of physics is a history of discovering those interactions and discovering the theories, the unified theories, that link those domains together, and therefore not just get more unified, but get more precise. And one reason why there is a strong expectation that this also works, let's say a strong a priori kind of expectation, why this also works in the case of quantum gravity, is that it has been so immensely successful up to this point. And what we will see in course of those lectures to some extent, what will be hinted at, let's say, is that also in the case of quantum gravity, there are reasons or there are indications that this works. It's not just hoping that it works, but there are indications that it also applies, even though it hasn't been proven yet. Well, so that was not included in the script, actually.
That was beautiful.
Thank you. So now let's start. And I think it's a really nice question. I think it's a great question as an introduction to all this, because this is about unification in the end. Okay, so let's start with the empirically well-confirmed part, or let's say foundation or basis of fundamental physics. And of course, there is a lot of empirically well-confirmed physics around, and I just want to remind you of those aspects in order to put what happens afterwards a little bit in perspective. So let's start with the theories of quantum mechanics and quantum field theory. The quantum mechanics, of course, celebrates its 100th birthday, so it is a time-honored theory. It is based on famous equations, and it characterizes the way non-relativistic microphysical objects behave. For particles close to the speed of light, however, quantum mechanics in its initial form doesn't work. It's a non-relativistic theory, so the equation must be replaced by relativistic equations, and those exist, were discovered soon thereafter for integer spins and for spin-half particles, famous Dirac equation I wrote down here. So these relativistic equations then provide the basis for what is called quantum field theory. Now, both of those theories, quantum mechanics and quantum field theory, of course, have a hugely impressive record of empirical confirmation. Quantum mechanics has been empirically confirmed by a huge array of experimental data, experimental tests of various folds throughout the last 100 years. And equally, quantum field theory has a very impressive record of empirical testing. In order to do empirical testing of quantum field theory, one needs to specify a little bit what one does with it. For example, if one wants to describe electromagnetic interaction, the theory of choice there would be quantum electrodynamics that was spelled out in the 40s in detail, and it has been experimentally confirmed at extremely high precision. It is the paradigm case of a theory that has been confirmed at extremely high, at the highest imaginable precision, let's say. To describe the other interactions that play a role in microphysics, a further step had to be taken. It was necessary to link those interactions to a generalization of the gauge symmetry that characterizes electrodynamics. Electrodynamics is a U1 symmetry, and it turns out that if one generalizes those two non-abelian gauge symmetries, one can characterize both electroweak and strong interaction in terms of those gauge groups. And these gauge theories that result from doing that provide the basis for modern particle physics, and specifically they provide the basis for the standard model of particle physics. So here comes the standard model, which is a gauge field theory and is based on this understanding that interactions are related to local gauge symmetries. And these gauge symmetries then are transformations that act on an internal space of particle degrees of freedom, and the standard model, let's say the core hypothesis of the standard model, is to state the gauge symmetry structure that characterizes the interaction structure of microphysics, of microphysical dynamics, let's say, at high speed. It therefore consists of three, the way it's written down here, U1 times SU2 times SU3, it consists of three simple Lie groups, as you say. And the particles then would be in representations of those groups. In this case, in the fundamental representation. The idea is that each of those simple groups then is related to one particle interaction. In the case of U1 and SU2, the situation is a little more tricky, which is why one talks about electroweak symmetry, but we won't go into those details at all. The idea here is, and what will be of importance later on, that each of those gauge groups has a charge. So each interaction, the particles that interact under that gauge group have a specific charge, and this corresponds to a gauge coupling that is a free parameter in the theory. So you can fit the theory to what you observe, the interaction strength that you observe. And what is the strength of the gauge coupling? The charge corresponds to, the strength of the gauge coupling corresponds to, is the strength of interaction eventually. So on that basis, we have here a standard model that predicts a set of particles, spin 1/2 fermionic particles, spin 1 gauge vector fields that are the carriers kind of the interaction, and finally a scalar field, the Higgs field, that is responsible for the mass spectrum. So the Higgs field technically is responsible for spontaneous symmetry breaking of the electroweak symmetry down to a U1. And this spontaneous symmetry breaking allows first that the W and Z bosons get mass, and second that the fermions have a mass spectrum rather than the fermions in the same multiplet having the same mass, which would be implied if the symmetry wouldn't be broken. So in other words, you need the Higgs particle in order to account for the observation that those masses are different in the fermionic case, and those masses are there at all in the case of the W and Z boson. So there is, it is a hypothesis how to account for the observations within the framework of the standard model. And so down there is the spectrum of the particles. Now, if we look at the empirical success of the standard model, of course, once again, this empirical success is really huge. So the standard model has been fully confirmed from the mid-70s to 2012, right? So there was a full list of matter particles that were discovered that fit into multiplets of the standard model gauge structure, so that works fine. The interaction strength of electroweak interaction fit the symmetry structure, that works fine. You get one could find the gauge vector fields, that was fine. One could also understand in terms of gauge field theory why there is confinement, why the elementary fermions that make up nucleons cannot be separated from each other. So this confinement is also naturally explained by the symmetry, by gauge field theory. That also works fine. And then, as a final step, in 2012, the Higgs particle, the scalar particle that is responsible for spontaneous symmetry breaking, was discovered. So that was kind of the final step for full confirmation of the standard model up to its characteristic scale that is called the electroweak scale. So the standard model is also a paradigmatic success story of science, one may say. Yes, if there are any questions about so far, yes.
Yeah, can you go back to the slides where you talk about the intensity of the interaction reflects the gauge, yet depends on the gauge coupling?
Yes.
Is that a definition, or how should I understand the strengths of the gauge coupling? Like, I see gauge as currency, so if you So
the gauge coupling, if you understand it at tree level, right? The gauge coupling characterizes the impact, so to say, the emission and absorption of a vector gauge vector boson has on the dynamics of the particles. So it is in a straightforward way, it corresponds to what would be an effective coupling of the process if you would not have the understanding that this is an exchange of the gauge field, of a gauge particle, right? So if you characterize the process as a contact interaction, you directly insert the coupling as the interaction strength. If you have a full fermion coupling, right? So the stronger the coupling is, the stronger you make the interaction. And now all you do when you introduce gauge field theory is you say, actually, if I look very closely, that for fermion coupling, so you would draw it like that, right? So that's the interaction strength. That's, let's say, call it G. And now what you do when you move from here to a gauge field theory is you notice that if those are fermions, this is not a renormalizable theory. So it doesn't really work. So you need to do something to turn that into a theory that is predictive. And what you actually do is you understand it in terms of an exchange of that vector boson. And here you have then the coupling constants inserted here. In other words, what controls the effect here is now kind of drawn out as an exchange of a particle of this vector boson. That's the rough idea behind this.
I don't know if you have ever heard of comparing this analogy of comparing gauge to currency. So I'm just I might being too simplistic if I understand the strength of the gauge constant as almost as the purchasing power of the currency. The stronger it is,
Well, that's the tree-level story, right? So of course, if you do quantum field theory, the story is not as simple because you sum up you sum up orders of interaction strength. So you get higher orders of interaction strength that also enter the picture. If the coupling constant is very small, those higher orders will be suppressed by orders of the coupling constant. So the tree level already gives you a reasonable picture, and the first orders of perturbation theory give you a highly accurate picture. If you move towards higher coupling strength, that's not the case anymore, right? So you lose the reliability of the perturbative expansion then. So if you this is, I don't know how much in detail we should go into that. What one can say is that technically you can always formulate the theory in terms of specifying the tree-level coupling at a certain energy scale. So the overall coupling is energy dependent in quantum field theory, in gauge field theory, due to the higher order corrections. So you can calculate the coupling strength at a different energy scale based on gauge field theory when you know the coupling strength at the initial energy scale. Yeah. And this is actually what you do calculate, right? So this is why this is not trivial, let's say, because if you just have the coupling constant at one scale, and that wouldn't change by energy scales, you would say, well, you just measure it, and you insert it here. The point is that you can only specify the coupling constant once, and then the energy running of the coupling constant is given by the theory. So the theory is highly predictive because of that. And actually that will be important later on when we talk about grand unification. Okay.
I'm sorry.
Yes.
This is done locally constrained, as it is a local gauge symmetry. Is the coupling also locally constrained?
Well, local. Yeah. I mean, the problem is that there are lots of technical terms here that I cannot. I don't have really the time to fully explain. But I can explain, of course, if you're interested. So the idea about these gauge symmetries, the way you deploy the gauge symmetries in the context of gauge field theories, is that so if you imagine a symmetry as a rotation in particle space. So let's say you have three particles, orthogonal directions, let's say. And if a theory is symmetric under transformations in that particle space, what you say is, if I rotate in that space, the physics doesn't change. Now, normally you would say, okay, I rotate once and for all. So I have one specification, what is particle A, B, and C, and then I rotate in that particle space, and that goes across the board for everywhere in our world. That would be a global symmetry transformation, if that was the idea. A local symmetry transformation amounts to saying, in principle, I can also specify the orientation of let's say the top quark in this two-dimensional space, top bottom, let's say. I can specify this separately at each point in space. I can say in point x, x1, x2, x3, I specify it that way. At a different point, I specify it differently. And it turns out that this is requiring this local gauge symmetry has very strong repercussions. It is what allows you to specify a renormalizable theory in the end, in non-abelian, based on non-abelian gauge symmetry. So it is local in this sense. It is local symmetry in this sense.
Okay. So it's not dealing with entanglement for the coupling.
No. Right. It's a different concept.
Thank you.
Can I just ask, so this locality requirement and like this general story of getting the proper Lagrangian from the group symmetry, it relies, it's basically like it's called a gauge principle and relies on this sort of
Yes.
thing, but it's been heavily criticized as sort of being like, by philosophers as being like anything more than just a sort of heuristic tool for getting to something which turns out to be nice later on. So isn't this sort of, what do you think, like, and then there has been attempts to sort of salvage the whole sort of principle, like, right, as a sort of legitimate, like, actually, like, relying on some sort of rational grounds. So, like in string theory and some other approaches, like this sort of symmetry first thing is very relevant for stuff. So like, to what extent, like, this, I mean, what's your opinion on like this sort of status of gauge principle as a sort of more or less being more or just like a heuristic tool, and like how it reflects the later sort of derivations like in string theory and like other.
Yeah, of course that's a great question, and it's a very deep question also. So with respect to, if we just look at gauge theories at the level of a gauge field, of quantum field theory, I would think that the reasoning that identifying a gauge structure is not relevant just doesn't go through, because what it does, it characterizes a specific situation of a quantum theory, or a specific feature of a quantum theory that in the end does have empirical implications, right? So it enters so there are two aspects in which it has empirical implications. First, the gauge symmetry may be spontaneously broken. So even though you have the gauge symmetry at the fundamental level, let's say the Higgs potential, the Higgs particle, and the potential it generates spontaneously breaks that symmetry, which means that if in our world we don't observe this gauge symmetry. We do observe particles, let's say up and down particles having different mass, for example. So there is no, they are not symmetric in our world. They are only symmetric at the fundamental level. Therefore, what eventually generates our perspective on the world is the ground state of the theory. So the symmetries of the ground state. And they may not be the symmetries of the fundamental theory. That would be the first response. The second response is, even if we don't spontaneously break the symmetry, so we have the symmetry, the gauge symmetry, also in the ground state, such as in quantum chromodynamics, nevertheless, the symmetry structure represents our way of counting events, right? It influences the statistics. Therefore, it does influence the outcome of our scattering amplitudes. So it does have, now of course you may say, well, but maybe I don't need the gauge field theory for doing that. I can find another perspective that does not rely on the gauge field theory and on the gauge structure. Yes, maybe, but show me one, right? So as long as that's the theory you have, and that's the formulation you have, it is that aspect of the theory that characterizes the observations. And if one thinks, so if one starts asking actually that's also just a preliminary answer, because then I would come to string theory or dualities where the situation gets even more interesting. But if I just look at it at that level, I might say I may not ever expect more from a scientific theory than that, right? It is, of course, if I'm a philosopher and I want to be let's say, a scientific realist about ontological commitment, then I may have problems with that. I may say, actually, I'm not sure about this ontology because it's so weirdly rooted. Should I endorse an ontology of gauge symmetry? I don't know. And that's where if one chooses to endorse such a position, then that generates trouble, right, for the philosopher. But that doesn't mean that gauge field theory or the gauge principle are not important for understanding the empirical import of the theory. Now the story becomes even more interesting once I move towards string theory, because in string theory we have duality relations, as we will see a little later, And those duality relations relate theories of different gauge structure. They relate a weakly coupled theory with one gauge structure, potentially, or in some cases, to a strongly coupled theory with a different gauge structure. So if you move them down towards the theory in a low coupling limit, you get a different ontology kind of out of that. And so if you want to be a realist about the ontology that is implied by your gauge structure, you don't find it. The fundamental ontologies are just different. Therefore, from that perspective, if you look at that, in a way, string theory and string dualities vindicate that understanding that gauge structure is not fundamental. It is not about fundamental structure because it can change actually with representation. So in a sense, those dualities give you a case where initially you said, okay, give me a different understanding of this that is not based on this empty fluff as it was called. And then the question is, okay, how could I do that? And at that level, one couldn't. But in the context of string dualities, you actually can. So the story gets more interesting in the sense that it is clear that you cannot be an ontological realist about gauge structure, or even a structural realist about gauge structure in a string theoretical context. Yeah. Yes?
Much of this will be parallel to ontological realism in terms of how we think about Middle's theorem or symmetries in more general, right? I think that's what has been discussed now in this case would be a specific instance of a more general kind of argument, right? Am I understanding right?
Well, it is. It depends on whether. I mean, if you talk about symmetries generally, there are also issues about global. I mean, this is a specific statement about local gauge symmetries. But you do get similar issues with respect to global symmetries as well. Yes, it turns out that at the fundamental level, you cannot identify global symmetries either. So it seems that it is justified in light of what you learn from quantum gravity to be skeptical about the fundamental ontology of symmetry altogether. Yes. Yes.
Just to make sure, so you said the second empirical consequences of gauges that a different choice of gauge will affect counting of states in thermodynamics. Did I get it right?
Yes. Yes. The fact that you have an SU3 in quantum chromodynamics enters your analysis of the diagrammatics, let's say, and therefore it enters the amplitudes, the calculation of quantum amplitudes.
So it's now gauge free, or is that because what we understand is physically significant?
I mean, it's not about, you don't identify the individual particles, obviously. This is not a broken symmetry or spontaneously broken even. So you don't identify the colors, let's say, right? So you don't identify one particle and can distinguish it from the other as a matter of principle. But the factor, there is a factor in your calculations that corresponds to the gauge group. Yes. All right. Good. I think I mean, just to announce this, we might have a 5 minutes break after an hour or so that we we don't get. Yes, we get some rest in between. And so I will try to be a little quicker here, because actually I want to focus on the new theories. And, and here I am talking about the empirically well-established one. So let me be very quick about general relativity and what comes afterwards. So of course, yes. So general relativity, as we all know, is the topical theory of gravity based on the understanding that that objects can move on geodesics in curved spacetime, and spacetime curvature is induced by energy density according to the Einstein field equations. And this, of course, has dramatic implications. And these implications have been confirmed, right? Lots of them. So starting with Eddington's experiments on light bending in 1919, that was the breakthrough for the theory in public perception, all the way to recent discovery of gravitational waves, and to the successful imaging of black hole, of course, with high, with a strong element of correction technology, let's say. Then we have the standard model of cosmology that relies strongly, of course, on general relativity, but also on lots of physical understanding about development of gases and planets, and on how all this works together based on our current understanding of physics. And this cosmological standard model also is in agreement with a vast range of cosmological measurements. One has to say that by no means all features of the observed cosmos are fully understood on that basis at this point, but one might be inclined to say that generally that is just what one expects from an empirically testable scientific theory. So there is lots of agreement, there are open questions, one tries to solve those open questions. That's what's going on. Okay, so the story up to this point is that there is, of course, a highly complex and empirically very well tested and very well confirmed set of theories that allow a certain degree of understanding of our physical world. Nevertheless, there are a number of quite substantial and fundamental new physical theories that aim at going beyond that understanding. And those theories, one can already say at this point, they are often based on either empirical anomalies or empirical, what looks like a very strange coincidence, right? A very unnatural constellation that seems to require an explanation. And those theories would aim at providing that. So I will very briefly characterize 5 of those theories, arguably the five of the most, let's say 5 of the most discussed theories of that kind. First, there is the issue of dark matter and dark energy. And dark matter and dark energy is to some extent is often subsumed under the set of empirically well-established theories at this point, right? So the standard model of cosmology nowadays is often called lambda CDM. So lambda for the cosmological constant and CDM for cold dark matter. So the understanding is that is already empirically strongly confirmed. And the basis for this is that observed galaxy dynamics, rotation is a little too narrow here, implies that there is more matter in the universe than what is visible. Now, that is the basis for conjecturing dark matter, for conjecturing that there are other objects that we cannot see. The measured accelerated expansion from 1997, on the other hand, strongly suggests a cosmological constant, which is also called dark energy. So before 97, there was, there were shifting preferences with respect to this cosmological constant. Some for periods, cosmological constant was considered helpful and attractive. Other periods, it was considered unhelpful. And different parts of physics, the views were sometimes conflicting on this. In 1997, it was established that there is this accelerated expansion, and it is conceptually mostly attributed to a cosmological constant. It is very difficult to find any alternative explanation of what's going on here. So on this understanding, only about 5% of the universe's energy content is visible on here. So if we ask once again the question of support for dark matter and dark energy, there is a lot of agreement between data and what dark matter can predict. And dark energy also is conceptually kind of, it's not directly implied by the measurement of accelerated expansion, but it is a very natural step to go. So this is taken to be very strong empirical evidence in favor of lambda CDM. Nevertheless, however, no scattering processes with individual dark matter particles or objects have been observed. So there has not been a discovery in the sense of particle physics, let's say. Therefore, the nature of dark matter is not known, and there are many candidates. It can be the lightest stable supersymmetric particle if SUSY is at low or middle energies. It can be axions, it can be other particles, it can be primordial black holes, so who knows, right? Therefore, dark matter has not been discovered in a narrow sense, but lots of exponents of dark matter would say that actually the gravitational effects of what is conjectured to be dark matter kind of amount to an observation themselves, right? So it has been observed in this sense. So it's well confirmed, empirically well confirmed, but not discovered. And that already should make us think about this rigid distinction, right, between empirical confirmation and no empirical confirmation. It's not clear in this case where we stand on this, right? Dark energy is, of course, a more complicated case. It can be represented in fundamental theory, so there are links to fundamental physics, for example, string theory. But its character at this point is not understood in any detail. It's not understood, for example, whether it is actually a constant, as the word cosmological constant would suggest, or whether it is slowly changing in strength over time. And that, on the one hand, once again, is an empirical question, and on the other hand, also is a theoretical question. There are suggestions from fundamental physics that might point in one direction or the other. Okay, so here now we come to an interesting aspect of this, and this aspect will be, we will follow this aspect, the aspect of alternatives throughout all those theories. There is a less popular alternatives, and in this case, one can clearly say it's less popular. It is probably, I don't know, 2 orders of magnitude at least different, if you count the number of physicists working on this, than those who in some sense work on lambda CDM inspired physics, let's say. So this is the idea, Mond is the idea, modified Newtonian dynamics, that initially it was the idea that you don't need dark matter at all in order to understand the dynamics of galaxies. You can modify the laws of Newton's laws for very small acceleration, and you get those results. The approach has lots of deep conceptual problems, and most of those problems are related to embedding this in a consistent way into the rest of physics. It's not clear what the fundamental physical representation of this could be at all. It's very difficult to find a convincing relativistic formulations. There have been attempts, but those attempts were not awfully successful. It fails to reproduce the dynamics of some galaxy cluster, in particular the bullet cluster, and it does not understand really large-scale cosmology. It cannot really link to global understanding of cosmology. So on that basis, most cosmologists consider it actually a refuted hypothesis. They don't consider it a rival theory anymore. A small group of supporters, however, views it as preferable to lambda CDM. And the reason why they do so is an interesting reason, and it will be interesting also for us. It is that Mond can explain some specific features of galaxy rotation, the flatness of galaxy rotation curves, that currently find no explanation in lambda CDM. So they have something, and that is kind of undisputed, right? That's not disputed by those who don't consider it a promising hypothesis at all. They can explain something that lambda CDM cannot. And where lambda CDM has to say, well, let's see, probably we don't understand the situation sufficiently well at this point. If you understand it better, some explanation should be forthcoming, because this characteristic is really conspicuous. So it's really something you want an explanation for, right? Roughly the point is that, that if you move from the center of the galaxy towards its outer limits, you would expect, normally we would expect that the further you move out, the slower the objects circulate around the center, right? But that's not what you observe. You observe that what is called a flat rotation curve, so the velocity remains the same. And the question is, so first it's interesting that this is the case. It has implications, of course, for the distribution of dark matter, if you think in terms of dark matter. But then the question is, okay, but why? Why is that the distribution? And dark matter modeling cannot come up with, they can reproduce it somehow, but they reproduce it just by mimicking it. And they don't have a substantial explanation why that's the way it works, right? Why that's the way galaxies are built. So what is interesting here, of course, is that even if a hypothesis explains something that the main contender cannot explain, I mean, there are some other explanations there are other ideas about how one might explain this, but let's say the main contender does not have an explanation. That does not rescue the hypothesis in this case, right? So the response of most of the physics community, cosmology community, to this is not, okay, so that's something interesting, maybe there is something to it, and maybe they can figure the rest out, which might be, at first glance, you might think that would be a plausible response. The response rather is, okay, yes, it can do that, but we are pretty sure that it cannot do all those other things. So it's nevertheless hopeless. That's that's the situation here. Moving on to cosmic inflation, and I think I stop after cosmic inflation for the break, maybe. Moving on to cosmic inflation. Cosmic inflation has been developed once again, because of observations, right? Because of observations that don't find a good explanation or didn't find a good explanation based on the canonical understanding of general relativity. And those observations are the isotropy of the observed universe and its flatness, near flatness. Now, in the early 80s, Alan Guth proposed an early exponential expansion phase of the universe that blows up early causally connected patches of the universe so that the entire universe that is observable today is causally connected. So therefore, he generates a situation where isotropy is plausible, even though it was not plausible without that phase. And it also flattens out the early universe. So he can explain on that basis those two characteristics. Now, a large majority of cosmologists today consider inflation likely. So they think that these arguments are convincing arguments in favor of inflation, even though, of course, there is no conclusive of confirmation of the theory. What I would want to point out also is that in brackets I always wrote the year or the period when those ideas were first discussed, right, or first presented. In the case of dark matter, dark energy, the concepts go back very far into the past. Of course, the cosmological constant was posited by Einstein himself when he presented this theory of general relativity. And dark matter was also discussed roughly in its current function already since the 1930s. Here, cosmic inflation has been proposed in 1981. And I already can point out that this is the youngest theory that we will be discussing here, right? This is the latest date when any of those theories has been initially proposed. So, yes, so that's the idea. Inflation has been proposed due to empirical observations, so there is kind of support of inflation on that basis, on that empirical basis. And it also agrees quite well with predictions of generic models with a cosmic microwave background. And what that means is that predictions of generic models of inflation agree with the cosmic microwave background because, as we will discuss in more detail than next time, tomorrow, there is a very high flexibility of model building in inflation. So there are some characteristics that work out very nicely. However, clearly, there is no indication of the actual field that drives inflation. So you need an inflationary potential that drives this exponential phase in a similar way as the Higgs potential breaks spontaneous symmetry. So you need this kind of thing that you can observe indirectly, even though you haven't identified the field that does it. And that's the situation we are physicists are in the case of inflation. There is a huge number of possible models of inflation because that mechanism is not empirically constrained that much. And there is no prospect that data can single out one or even a small set of models in the foreseeable future. exponents of inflation argue that no promising alternative to inflation exists. So once again, we have a situation comparable to the dark matter situation, where dark matter say that that's the only thing that works. Therefore, we should endorse it. Similar things have been said just as strongly, one may say, by leading exponents of inflation. On the other hand, once again, there are alternatives, right? Alternatives have been proposed, quite some of them in this case. I just state the name of two of them, but there are more. So there is this spectrum of alternatives that are favored over inflation by their respective exponents, but are considered less than promising by most exponents of inflation. And if you ask them, they can give you specific reasons why they think so. Now, these ideas, these alternative ideas, are supported by substantially smaller groups of physicists than inflation, once again. It's probably more than one order of magnitude. I don't want to compare this now to the Mond case, but these are also quite small groups that work on it. But some among those who work on it are some highly prestigious physicists, which is why those alternatives are taken more seriously, probably. And so some physicists who contributed substantially to mainstream physics endorse some of those alternative approaches in this context. Good. Okay, so let's continue with two theories that focus on beyond the standard model physics. So they also are kind of let's say grand unification has no immediate relation to quantum gravity, but it may be related to quantum gravity in a string theoretical context if there is because there may be a string theoretical reason for grand unification. So the idea there is, once again, the reason why this is interesting and why people think about it or thought about this is entirely empirical, right? And that's something that one needs to point out here, that the observation, in many cases, there are observations that trigger these investigations. So observations about the dynamics we observe in the cosmos, or observations about these characteristics such as flatness and anisotropy. Or in this case, if we go back to the standard model, and you remember, and now I've presented that already to some extent. If you think about standard model physics and the gauge coupling constants, those gauge coupling constants are not constant over energy scales. So they, as it is called, they run over energy scales. They have a characteristic value given a specific energy scale. And the structure of the theory tells us how they run. And if one calculates this running of gauge couplings based on what is called renormalization group methods, you find that those couplings seem to, let's say, I don't know what the nicest way of presenting this, but they seem to try to meet but just barely miss, right? Those are the three couplings for electromagnetic, weak and strong coupling, and the approach each other and roughly meet. And this is already this is not accurate as one can observe here. It may not need to be accurate because there is what is called threshold effect. So close to to their meeting point, if there is a grand unified theory, there may be some things that change. And therefore, there may actually be a genuine meeting point that we don't see from our low energy perspective. So that may be good enough, but it's a little, not even taking that into account, it is the most plausible structure, let's say, but still it's conspicuous that they meet as well as they do. It's not highly probable that coupling constants, if you think about the probabilistic distribution, if you interpret parameter space probabilistically, let's say, and think about how probable is it that exactly those values are chosen that generate such a meeting of gauge coupling to the extent they do here, it's not very likely. It's quite unlikely, actually. So it is something that seems to require or may require an explanation. Of course, it doesn't have to. It's not that accurate, right? It is, so if you ask the question, why does the moon look roughly as large as the sun from our perspective, that would be a comparable degree of accuracy, let's say. So it's not clear that we need it, but there is something else. And this something else is that the observed fermions fit into representations of a simple larger gauge group. And that's also quite non-trivial. It's not likely. If you think, once again, if you try to think about all the options one might have to have particle spectra in the standard in low energy physics, it's not at all likely that this happens. It's a similar improbability. And if you have two things of that improbability and they point at the same direction, you start thinking, okay, I mean, this is really weird, right? This is very strange. The possible explanation is grand unification, right? The interactions we observe at low energies are the remnants of unified interaction structures at high energies. So if we have grand unifications, that means, or let's say the most straightforward way of representing it would be that there is one big gauge group at this high scale where the couplings meet, that is called the gut scale. And all the particles are up there in representations of that big gauge group. And all what we see today at low energies, that's just the low energy remnants of that big gauge group. And we see that because this gauge symmetry that is in effect at the high energy scale is spontaneously broken for some reason, whatever, something like, once again, something like a Higgs potential or some string-induced symmetry breaking mechanism, whatever. So that's the idea. The point is that this looks like fairly strong empirical support of something like this. So it is, if you take this together, you have two fairly strong empirical coincidences that find an explanation on that basis. There is one possible implication of grand unification that was hoped to be observed early on when after GUTS had been proposed, and this is proton decay. Proton decay depends on the characteristics on the specific symmetry group and the overall symmetry structure. And it turns out, so the simplest gauge group would predict that one can measure proton decay, and it was very much hoped that that would be that could be observed, but it hasn't been observed up to this point. So there is something that rules out observations that rule out the simplest gauge group of unification, but it leaves intact others. So it is not a refutation of grand unification, it is a refutation of that specific form of grand unified symmetry structure is SU5. Yes.
Richard, but this new kind of good were formulated after that we didn't find the proton decay or before?
Before. So the two main, let's say, most straightforward grand unified gauge groups, which are SU5 and SO10, they were basically proposed at the same time. Initially, some people thought that SU5 is more attractive because it's simpler and it allows for being empirically tested, right? And then there is another element to this, which is that one can think about grand unification in a supersymmetric framework and in a non-symmetric framework. And that also changes the understanding. Supersymmetric grand unification tends to be less favorable to proton decay. So that even makes this space of options wider. Okay, so if we ask for alternative explanations here, the answer is, and this is a little overly pointed, let's say, because I like this. There is one case where one can say, if I take these two observations and I ask, is there any alternative that can account for that? The answer is actually no. You can say it's pure chance, but there is no other theory that does that. There is, if one just focuses on the unification aspect, the answer would be yes, coming from high energy scales, because a string theory does not imply a grand unified theory. String theory can generate a unified gauge coupling without a grand unified symmetry group. But that leaves the question, okay, but so now why are those particles in these fitting representations? And if you add that to the story, which of course is very plausible, you end up with, in any way, with something like a grand unified theory. So in this case, it is difficult to think of other ways of thinking about this. The second case I wanted to talk about is supersymmetry. And of course, supersymmetry was highly popular recently because everyone hoped that it would be found at low energies at the LHC. If we look at the time when supersymmetry was proposed, this is 71 to 74, initially coming from various directions, one of those directions being string theory, early string theory that is, and in 74 it was formulated as a genuine space-time symmetry of our four-dimensional space-time. So that's the period when the idea was created. When we go back to GUT was also proposed in 74, right? So we are early 70s now that those theories have been proposed, 50 years ago. So supersymmetry introduces a new symmetry. At this point, this is a global symmetry, stating that for every fermionic particle, there exists a corresponding bosonic one, and vice versa, obviously. So these are the super partners. This means if this is realized in our physics, it is clear that none of the standard model particles can be combined into, can be viewed as superpartners of each other, which means that if supersymmetry is the case, all the particles we know need to have a superpartner that has not yet been discovered. The idea how this can work is that once again, this symmetry, the supersymmetry, is spontaneously broken so that the superpartners are heavier than the standard model particles. If one asks, so why is this an attractive idea? There are some, let's say, conceptual aesthetic ideas, which I don't want to go into here. One reason, if one endorses string theory, is that supersymmetry is a necessary ingredient of string theory, at any rate on a canonical understanding of string theory. This, however, does not mean that supersymmetry is somewhere close to the electroweak scale. So it can be a structure that is already broken at the string scale, so there is nothing for us to observe about string theory. If we think about the question, is it plausible, or why should we expect that supersymmetry can be found at lower or medium energies? That is, why did one think that it can be found, could be found at the LHC? And now, why could one think that it would be found if we built an even larger particle collider? First, supersymmetry at lower or medium energy, so this can be energies quite some level up from the one tested so far, improves substantially the gut behavior. So if we add supersymmetry, actually we find basically nearly an exact meeting of the gauge couplings. Given that if one assumes that grand unification on its own is supported by the data, that's a quite considerable argument in favor of supersymmetry. And actually, with James Wells, we modeled credence in supersymmetry based on these various factors. And one result of these models is that on most, or any, on our view, plausible model, actually the gut behavior is the biggest driver of credence in supersymmetry. It is kind of it looks like the strongest argument in favor of supersymmetry. If we think about the dark matter issue, SUSY also would fit nicely because it could be, there might be in some plausible, let's say in one plausible class of supersymmetry models, there would be a lighter supersymmetric stable particle, and that would be a plausible dark matter candidate. So supersymmetry could also solve this issue, even though one has to say there are other candidates as well. So the strength of that argument is not entirely clear, let's say. The reason why everyone or so many physicists expected that supersymmetry would be found at the LHC is the issue of the naturalness issue. So the question why the electroweak scale is so far lower than the Planck scale. And this separation of scales looks very strange in quantum field theory, in particular if we assume that there are massive scalar fields up there, because these massive scalar fields would destroy order by order the separation of scales. So it looks very strange to have it, and of course it also looks strange anyway to have this separation of scales, as long as one cannot explain it in terms of something like a running of a gauge coupling, right? So if you have only, I mean, this is a little too, maybe I shouldn't go into the technical aspects of this, but if you have characterize a running of a gauge couplings, what contributes to that running would be logarithmic contributions to the in perturbation theory. And the problem when it comes to the separation of scales is that in this case, due to scalar contributions, this doesn't work. You get quadratic contributions. You expect quadratic contributions of the higher orders, and therefore it is not plausible to separate those scales as long as those quadratic contributions don't cancel off. And now it turns out that supersymmetry does exactly that. Supersymmetry would cancel off exactly those quadratic contributions that destroy the separation of scales. And when this was understood, it was taken to be a very nice reason or strong reason to expect supersymmetry to be discovered. Because only if supersymmetry is being discovered close to the electroweak scale does this work, right? Otherwise, it would not work, because then one wouldn't have the quadratic contributions of the very high scale, but one would have quadratic contributions of this symmetry breaking scale. So one would have the same problem, basically, a little less dramatic way. And that's the situation one finds oneself in today, since the supersymmetry breaking scale based on empirical data from LHC has to be at least a little higher up. So there is the hope that supersymmetry can reintroduce naturalness in our understanding did not play out. Therefore, that's one reason why supersymmetry today is considered less promising, or the empirical evidence is considered less convincing than it used to be before the LHC. Any questions on this? Yes?
Well, the LHC hasn't found any supersymmetric particles at these low energy scales, hasn't it?
Right. Yes.
That's why.
Exactly. So sorry, I did not explicitly say that. Right. So they hoped that they would find it, but they did not. Yes. Karen, and then yes.
Yeah, I was just curious about the grand unified theory, so before getting to this.
Mm-hmm.
Because we often hear that no one's really, this was a thing and now it's not.
Yes.
Why?
Yes, I come to that in a moment. Yeah, I think it's an interesting story.
Yeah.
Yes.
Yeah, I think it's still a thing for a lot of string theorists, as far as I know. But I'm much more interested if you are willing to share your opinion about the superstring argument, and if it's there or not.
Superstrings? No. Or supersymmetry? No, I don't think so. So I would say that I can tell you what we did this assessment in order to propose a, let's say, a quantitative account that can suggest a development of credence in supersymmetry. So of course this is based on estimates, on priors, and so on. And therefore, it doesn't give you one result, obviously, but it shows a spectrum of results, and it shows some kind of convergences of behavior of credences. And what we find is that there is a decrease in credence on any account, on an account that started from an optimist expectation regarding SUSY, and also accounts that start with a pessimistic expectation. So there is this decrease, but it is not awfully substantial, it turns out. And there are some reasons for that. One reason is that the main driving force is actually gut on any of those accounts, and that hasn't changed. The second point is that there is one aspect of LHC data that actually increases credence in supersymmetry. That's the Higgs mass that is consistent with SUSY predictions, which SUSY predicts a narrower Higgs range than the standard model. So there is this aspect. The other aspect is that the naturalness argument is a tricky argument, right? And it has more. So the way we try to model this is in terms on one needs to model it in the end is in terms of assessing the spectrum of other options. And when it comes to naturalness, it is not, naturalness is in a different conceptual situation than, let's say, the gut arguments. The gut arguments have a fairly straightforward parameter space, and the question is whether there are theories that can change the measure on that parameter space in a way that makes this natural. And so you can say, no, we can't think of any, right? So that is a theoretical perspective on the issue. When it comes to the naturalness issue, the point is that there is no full theory that establishes the quadratic, the relevance of that particular measure on parameter space at all. So you need to think about the fundamental theory in order to answer the question, is it plausible actually that this measure is linear on energy scales or not? So, and there are some considerations that it may not be, right? Considerations that may be rooted in the fundamental theory. So it's more difficult to gauge the significance of naturalness arguments. And that, of course, is represented in the discussion on naturalness that is actually going on. So there is a plausible hypothesis that the fundamental theory, the true fundamental theory, won't support this quadratic measure on this. The reason why this is, I mean, yeah, I don't want to go into too much detail here, but this, to some extent, it does not remove the argument at all, but to some extent it weakens naturalness arguments from the start over straightforward parameter space arguments that play out at the electroweak scale. So in one simple way of putting it is that when it comes to those parameter values that characterize gut behavior, it is not plausible to think about high energy physics that can change the measure on those parameters. It is, while with respect to naturalness issues, the question is more open. And then, of course, you also have you have anthropic options and so on. In other words, even though there is a substantial decrease in credence due to the failure of the naturalness argument, it does not destroy the significance of those other arguments. So there is a remaining credence in supersymmetry that remains quite significant, I would say. That is low energy supersymmetry, or low and mid energy supersymmetry. So supersymmetry at an energy scale that can still work as being conducive to grand unification. Yes.
I remember just one aspect of the naturalness problem. Because if I'm not wrong, the argument usually is like we have a renormalization of the mass, we have loop contributions, and we have no reason to think that the contribution should be not so high, right? So we are like surprised that the Higgs mass is so low, usually. But we also know that quantum field theory should break down at very high energies, so why we are surprised that of this thing. So we have this renormalization, these loop contributions.
Yeah.
Because of these loop contributions, because we have no reason to think that the contribution should be not so high, we are surprised that the mass is so low.
Yes.
But we also know that when the contributions are so high in energy, we know that as an effective field theory, our theory is not so reliable. So I cannot understand why the naturalness problem is so peculiar as a problem. I don't see something very peculiar in this problem.
So I mean what normally what you have, or generally what you have, the reason why you can think of low energy physics in a way that is separate from the high energies is that if you just look at the low energy phenomenology, the contributions from the higher scale will be suppressed by that higher scale, right? So the quadratic contributions that, for example, enter in terms of mass terms of those higher particles, they would be suppressed by the masses of those higher particles. So that is why one can, in a reasonable way, do physics based on the particle spectrum, on the light particle spectrum. So those high mass particles, for example, they do contribute to some extent, but only to a very low extent because of this suppression factor. Now, if one thinks about the naturalness issue, the question is a different one. The question is the stability of the low energy potential, the low energy Higgs potential that is shielded from the scalar potential at the higher energy scales. And for technical reasons, there is no shielding effect at that level. So if you think about potentials that break the symmetry structure at low and at high energies, you need a good reason why this breaking at high energies doesn't pull up all the spontaneous symmetry breaking potentials. That's the problem, let's say. And if one finds a solution where one can point at a symmetry that makes those contributions from the quadratic contributions from the high energy scale cancel, then you have an answer. Then you say, okay, they don't appear because of that symmetry. And it turns out that symmetry, supersymmetry would be, or would have been, let's say, that symmetry. But it didn't work. Or it did not agree with observations in the end. All right, yes, so empirical support for supersymmetry, as said, is mixed. On the one hand, there is still the argument of gut behavior and the correct mass range for the Higgs. However, supersymmetry has not been found at the LHC, despite high hopes due to the naturalness argument. So if we think about alternatives to supersymmetry, the story is a little different from the other cases because supersymmetry does not have one core problem that it was developed to solve, right? It was developed for other reasons, then was considered, then it turned out that it can play an interesting role. In the context of the gut scale, supersymmetry very strongly improves the meeting of the gauge couplings. You could, however, also imagine other structures doing something comparable, maybe not. It would be difficult to come up with something that works as well, but maybe that's not even needed. You might also say, actually, the threshold effects at the gut scale are so strong that just the standard metal alone gives us the correct dynamics up to that high energy scale. So yes, so there is substantial support from that direction, but there are also alternative proposals, and they are not considered implausible by anyone, right? So it's not this situation that we have encountered before, where there is a dominant theory, and exponents of that dominant theory would claim that the alternative solutions just cannot work. That's not the scenario in the situation in string theory. So everyone, in supersymmetry, everyone would concede that those can work. And the same goes for dark matter. There are very plausible dark matter candidates, and no one knows which one is right. And even also with respect to the Higgs mass, of course, the Higgs mass constraints from supersymmetry are not that great or not that precise. There are other approaches that generate similar constraints. So there is no reason on that basis to rule out alternative approaches. So which means that there is no lack of alternatives in any of its roles for supersymmetry. What one might say that in conjunction, these empirical observations might generate a certain degree of credence in the hypothesis. That would be the current situation. So, okay, so we are nearly out of time, I think. So I just, maybe, yes, either I start talking generally about quantum gravity a little bit, or I do that next time. Maybe it's topic-wise, it might make more sense to discuss the last minutes about what has happened, and then I continue next time with this. So yes, so let me just ask you whether there are any questions or comments on what has happened so far. Yes?
I have a general question, I guess, but because we're now talking so much about SUSY, and we have the LHC and particle colliders, and then we didn't find superpartners. So what I'm curious is kind of, since you have this very good overview, basically.
Oh, thank you. Do you think that the bigger particle collider will do what is needed to help us kind of advance this? Do you think it's more theoretical work, or is it, as a third avenue, just different classes of experiments and different kinds of avenues to investigate, or all of those?
So I would think that for this variety of reasons that I suggested or I presented, supersymmetry still is the most promising perspective on beyond the standard model physics. The problem is that even if, so it's not clear. I mean, there are various suggestions with respect to the size of the next collider. It is not at all clear whether the smaller of those versions would reach scales, even if supersymmetry did play that role. Let's assume supersymmetry actually is responsible for improving gut behavior, and let's even also say that supersymmetry at least provides one component to dark matter. It's not clear that, for sure, it's not. One wouldn't bet on the smaller versions finding supersymmetry. Even the most extensive versions might miss it. They may have a better chance, maybe a good chance. I'm not the person to assess this for sure, but it's not clear that they can exhaust the range of supersymmetry. I mean, there are. So there is a different aspect to this discussion, which is the aspect of the SUSY breaking mechanism. And there are very roughly two types of mechanism. One of them would very strongly suggest that one should have found it if that was applied, because it's fairly directly linked to electroweak symmetry breaking. And the other makes it plausible that, or actually kind of predicts that there is a separation of scales between the supersymmetry breaking scale and the electroweak scale. And so one would expect that mechanism to be more promising at this point. But if that's the mechanism that it is played, yeah, it's not clear whether one might find it or one might not. I think there are no strong statements from theoretical physicists that comparable to the previous case that if we build that collider, then we would find it if it's there. It may happen or may not.